Okay, now we're getting to some more fun stuff. This is part 4, where we're going to start describing the kinetics of catalyzed reactions. So we're going to calculate the kcat, km, and Vmax using plots or the Michaelis-Menten equation. We're going to interpret the turnover, Michaelis constant, and catalytic efficiency of enzymes. Okay, so starting off, this is our general equation for a catalyzed reaction done by an enzyme. We have enzyme, we're adding in the substrate. This goes forward at some rate k1 and goes reverse at some rate k minus 1 to create the enzyme substrate complex. Then, through the kcat, this enzyme substrate complex will then become the enzyme plus product. This is essentially irreversible. So this is why the kcat is drawn just in the forward direction, but the k1 to the k minus 1 is reversible in that way. Because the substrate combined, and as long as it hasn't become product, the enzyme substrate complex could either fall apart or it can go forward. So there's a beautiful derivation of this in your book. We get the rate of this reaction can be described as the maximal velocity times the concentration of the substrate here over the km, which is a ratio of all of these kinetic constants, k1, k minus 1, kcat, plus the concentration of substrate. And so this is the Michaelis-Menten equation. And again, there's a beautiful derivation in your book, and we'll probably do it in class as well. And when we take this Michaelis-Menten equation and make a plot of it, we find that this shows a hyperbolic curve, right? Okay. So this is the reaction progress for an enzyme catalyzed reaction. So we've got the concentration of substrate increasing across the bottom, and we've got the velocity increasing along the y-axis. Okay, so from this, the maximal velocity, or the Vmax, is the top point of the parabola. Okay. The km, where can I write this? The km is defined as the concentration of substrate at 1/2 of the Vmax. So, for example, if this number is 1, then half of the Vmax would be 0.5, and you would trace that out to the line. It's right here. And so the concentration of substrate at 1/2 of the Vmax is whatever this value is. This value would be the km, this concentration of substrate. So that's all well and good, but the Vmax is not the best way to go about talking about enzyme kinetics here. Because if we decrease the amount of enzyme by half, the Vmax will decrease by half. So this would be our new Vmax, right? So that's not very good. So the Vmax depends on the amount of enzyme in the solution. So if we doubled it, it would be twice. So the Vmax doesn't tell us anything specific for the enzyme. So what we did instead is we came up with this idea called kcat. So this is the turnover number, or the catalytic constant, of an enzyme. And we calculate this based on the Vmax. So we take the Vmax and we divide it by the total concentration of enzyme. And we know this because we know how much enzyme we put in the tube. So this is much better than Vmax alone because this number doesn't change. This number takes into account the amount of enzyme that you put into your tube. Vmax changes based on the amount of enzyme. Okay, but this takes that into account. So kcat is really, really great. Okay, so kcat is typically reported in units of seconds to the -1 because this is a first order rate constant. This kcat right here looks at just the degradation of ES into E plus P. So this is a first order rate constant, that's its units. So the larger the number of kcat, the faster that this enzyme goes, the faster that this works to perform the reaction. So a larger number is better. Km is a little difficult to interpret because it's defined as, the concentration of substrate, but what does that really mean? Right, the concentration of substrate at 1/2 Vmax. Okay, great. What does that mean? This kind of means how well something's going to be bound. And true enzymologists rarely interpret this very strictly. Okay? So this is somewhat related to binding. Right? Because if we look at, this is the ratio of all of these things. This is, the on versus off rate here, but it's also related to catalysis. So it's kind of how much of the substrate makes it to product. It's related to that, but it's very, very difficult to interpret as is. What a lot of biochemists use the Km for is you compare the Km to the concentration in solution. Compared to the concentration of substrate, for example, available in the cell. In the cell. Because when we have a lot available in the cell, we're hitting the maximum rate, right? So as we increase the concentration of substrate to infinity, we are at Vmax, right? So as long as there is more in the cell than the Km, so the Km is kind of used to determine how much more you need to add into your reactions if you're doing this in vivo, but you also compare it to how much is available in the cell, and there better be more available in the cell so that you know that your enzymes are at Vmax. They're working to their maximum potential. Yeah. So another way of saying that is, as we increase the substrate, we hit the Vmax, so you better make sure you have way more substrate in your solution than the Km value. Because otherwise, you're never going to calculate Vmax. Right? So if you have to do different tubes of solution, each one of these lines is a tube, right? If you stop here, you're not at Vmax. You have to keep going, keep adding more substrate until you hit at least close to the Vmax. And so we use the Km to determine the concentration of substrate we need to hit the Vmax. Okay. And there's one more thing that I want to talk about, and that's the ratio of kcat to Km. And that's the idea of catalytic efficiency. So that equals kcat over Km. So after you find the kcat value and you find the Km value, you divide it. And you'll get 10 to some number, probably, if your enzyme is good. And 10 to the 8th or the 9th is perfect. 10 to the 8th or 10 to the 9th. This means that your enzyme is actually limited by diffusion. So how quickly the substrate can diffuse through the liquid to get into the active site, it can turn it out and make a product. Okay. Units here are typically molar to the -1, substrate to the -1, because the units for Km are molar, units for kcat are seconds to the -1. I said substrates to the God. Molar to the -1, seconds to the -1. Units for catalytic efficiency. So these numbers are ideal. And the closer it is to this, the better it is. The better your enzyme is at turning over the amount of substrate that it's given.